Welcome, everyone. I am absolutely thrilled to have you here for this explainer. Today, we're taking a seriously focused, deep dive into one of the most fascinating frontiers in modern engineering. We are demystifying advanced mechatronic synthesis and really exploring the bleeding edge of high-performance hardware. So, I want you to get ready because we're about to unravel a massive mechanical mystery, one that literally dictates how the most advanced machines in the world interact with their environments.
Picture this for a second. A heavily armored, 200-pound robot dog leaps into the air and crashes back down onto solid concrete. Now, logically, the immense kinetic energy from that impact should travel straight up its metal legs and instantly shatter the delicate, high-precision gears spinning inside its motors. It's a massive clash between heavy, dynamic machinery and super fragile internal mechanics. And yet, the robot simply absorbs the shock, stabilizes, and keeps right on trotting along. So, how is that physically possible?
Okay, let's dive into this because the answer to that seemingly impossible hook is something called actuator compliance. This right here is your aha moment from modern robotics. Traditionally, we think of machines as rigid, stiff, and unforgiving. But actuator compliance is a designed mechanical property that allows a robotic joint to actually flex and yield to external forces. It basically acts as an impact absorber. Without this built-in flexibility, dynamic movements like jumping, running, or even just walking on uneven terrain would literally tear a heavy robot apart from the inside out.
Section 1. The anatomy of compliance.
Let's move to and see how this builds, looking specifically at the Series Elastic Actuator, or SEA. This is a brilliant design secret used by roboticists, and it's basically a three-step system. First, the motor generates the raw rotational torque. Second, that power moved into a gearbox which multiplies the force so the robot can actually lift its own weight. But here is the genius part, step 3. Instead of rigidly connecting that gearbox directly to the robot's leg, engineers place a tuned spring mechanism right in between. That spring is the magic ingredient. When the robot's leg hits the ground, the spring compresses, swallowing the shockwave completely before it ever even reaches the fragile teeth of the gearbox.
Moving on to Section 2, high-performance hardware solutions. Now, the spring protects the gears, sure, but to generate the immense power required to throw a heavy machine into the air in the first place, engineers must flawlessly balance 3 essential pillars. First up, power-to-weight optimization. Your motor must be incredibly strong, but incredibly light. Otherwise, the robot just spends all its energy lifting its own components. Second is brushless DC, or BLDC motor physics. These motors use electromagnetic fields rather than physical brushes, completely eliminating friction and unlocking massive rotational speeds. And third, 3D printed reducer geometries. This is all about utilizing modern manufacturing to create really intricate, custom gear systems that perfectly match the robot's unique anatomy.
If you look closely at our source material, you might actually remember a multiple-choice practice quiz question asking about the primary benefits of quasi-direct drive, or QDD systems. Well, here is your answer. QDD combined with cycloidal reducers is the absolute secret sauce of high-torque, compliant joints. Instead of using massive, heavy gearboxes that take up a ton of space, QDD uses a motor connected to a low-ratio cycloidal reducer. And these cycloidal reducers use this mesmerizing, kind of wobbly disc motion to multiply force immensely while staying incredibly compact and lightweight. It gives you the immediate, snappy response of a direct connection with the raw lifting power of a heavily geared system.
And this brilliantly illustrates exactly how engineers size those motors perfectly. They use a motor torque speed curve matrix just like this one. So say you're sizing a motor and trying to find the gear ratio for a 5-degree of freedom robotic arm. You look right here. When the arm is starting up or lifting a heavy payload, it operates in a state of high torque but low speed. Once it's up and cruising, the torque drops to a moderate level while the speed increases. And then for rapid positioning like darting back and forth empty-handed, you need high speed but very little torque. By analyzing this operational matrix, engineers can pinpoint the exact QDD system and cycloidal gear ratio needed to make sure the arm performs flawlessly across all these totally different states. But wait, I really need to pause right here and slow down, because there is a massive trap waiting for anyone designing these systems. Do not overlook the thermal limits in high-performance BLDC motors. Pushing massive amounts of electrical current through these tiny, compact motors to get that high torque generates just an unbelievable amount of heat. And because they are so small and densely packed, they can and absolutely will melt their own internal wiring if they're pushed past their thermal breaking point during sustained high-performance tasks. You literally have to design for heat dissipation just as much as you design for power. Let's look at Section 3. Case Study, James Bruton's OpenDog V3. A really fantastic, tangible example of all this from our source material is James Bruton's OpenDog V3 project. It proves that all these complex physical calculations actually result in functional real-world hardware. This robot utilizes custom 3D printed cycloidal reducers to achieve dynamic, perfectly balanced walking gaits. It's a heavy machine lifting itself, balancing and absorbing impacts with every single step. And you know what's most exciting here? It proves that high-performance, compliant design isn't just locked away in multi-billion-dollar corporate labs anymore. It is becoming highly accessible to everyday engineers using modern desktop manufacturing. Now, the reason a robot like OpenDog V3 can walk safely without shattering its own legs is heavily dependent on a concept called backdrivability. Simply put, backdrivability means that if you push on the robot's leg, the joint will smoothly yield and actually spin the motor backward rather than locking up and breaking the gears. If a joint has high backdrivability, it's inherently compliant. When the robot's foot hits the ground, the impact force drives the mechanism backward just a fraction of an inch, gracefully absorbing all that kinetic energy.
Section 4. Rigid versus compliant robotics.
This brings us to a structural comparison that represents a massive evolutionary leap in the field. So, the crucial point is the paradigm shift we see right here. For decades, the absolute industry standard was the rigid industrial arm. These are built for high precision, moving to an exact millimeter coordinate over and over again in a controlled factory setting, but they are incredibly stiff. If a rigid arm accidentally collides with something, it is highly prone to literally shattering its internal gears. On the flip side, we have compliant, bio-inspired machines. They trade that millimeter-perfect precision for shock-absorbing, backdrivable, dynamic movement. They are specifically designed for the unpredictable, chaotic real world, functioning much like biological muscles and tendons do. And why does this all matter to us? Because compliant technology isn't just about building cool robot dogs. This is the foundational hardware required for the future of advanced prosthetics and humanoid design. Think about it. A prosthetic limb cannot be stiff and rigid. It absolutely must yield as the user walks down stairs or steps on uneven ground, so it feels natural and safe. Similarly, humanoid robots operating in our homes or hospitals need to be compliant, simply so they don't cause damage when they inevitably bump into furniture, or, much more importantly, people. Now, what's really interesting about this slide is if you want to master the specific structural trade-offs required to actually build a bipedal humanoid, our source material directs us to some essential reading. Humanoid Robotics Hardware by Lee and Kong. This is an incredible deep dive into how to integrate QDD systems and backdrivability into a human-scale frame. So if you want to take your learning to the next level after this explainer, that is absolutely your next stop.
To wrap up our explainer today, I really want to leave you with a provocative debate question raised right from our source material. As we've seen with projects like OpenDog V3 utilizing custom-printed reducers, we really have to ask, will 3D printing eventually replace traditional CNC machining for professional, high-performance robotics? The line between prototyping and end-use manufacturing is blurring faster than ever before. Think about the trade-offs in materials, speed, and precision. It's a fascinating question, and one that the next generation of engineers is ultimately going to have to answer. Thank you so much for exploring the dynamics of mechatronic synthesis with me today. Keep learning, keep questioning, and I'll catch you next time.